What really causes the ocean to rise and fall? It's a pretty fundamental question, isn't it? I mean, if you stop someone on the street and ask them, they'll probably say, oh, it's just the moon's gravity. And, well, they aren't completely wrong, but there is so much more to it than that. Most people don't fully understand the massive churning and honestly sometimes terrifying physics that are actually at play here. We're talking about a wild story involving planetary spin, centuries-old historical mysteries, and just immense geographic power.
So, welcome to this explainer. Today, we're literally decoding the cosmic pulse of ocean tides. We're going to take the raw data, look at some fascinating physics, and uncover what's really controlling our oceans. Let's dive right in.
Here's our quick roadmap for today. 1. The pull of the ocean. 2. Gravity, spin, and history. 3. Spring and neap tides. 4. Earth's extreme tidal monsters. And 5. Harnessing limitless ocean energy.
Let's kick things off with Section 1. The pull of the ocean. Okay, so build a rock-solid foundation for this. Let's just define what a tide actually is. A tide is the periodic rise and fall of sea levels. But I want you to notice the massive variables at play here. It's the gravitational interaction between the Earth, the Moon, and the Sun, and all of that is combined with the Earth's rotation. It's absolutely not a static pull. It is an incredibly dynamic, constantly moving system. But how exactly does this create the 2 daily high tides that most of the world experiences?
Well, think of a rotating water bottle. Imagine you're holding a water bottle and you start spinning in a circle. The water pushes outward against the plastic, right? On Earth, the side of our planet facing the moon gets pulled outward by lunar gravity, and that creates a bulge, which is a high tide. But because the Earth is a rotating body, on the exact opposite side of the planet, a centrifugal force balances this whole thing out, essentially throwing the water outward to create a second equal bulge. So gravity pulls it on one side and the spin throws it out on the other. Water is literally pulled from the adjacent areas, creating low tides right in the middle. It's a stunning planetary balancing act.
Moving right along to Section 2, Gravity, Spin, and History.
So let's rewind a bit. Back in 1687, Sir Isaac Newton published his monumental work claiming that gravity, this invisible attractive force between bodies, was what held the universe together and governed our seas. He used impeccable, groundbreaking mathematical models to prove that celestial bodies pull on the ocean. But here's the fascinating catch. Newton had absolutely no idea what gravity actually was, or why it affected water so dramatically but didn't seem to, yank solid objects around on the shoreline in the same way. He just knew the math worked perfectly.
And because Newton couldn't explain the why behind gravity, other brilliant minds offered up completely different theories. I mean, some scientists argued entirely against Newton's math. William Gilbert proposed a geodynamo theory, basically claiming the Earth was a giant magnet and the tides were governed by magnetic forces. René Descartes went even further, proposing this wild universal vortex theory where the sun generated a swirling magnetic medium that drove the planets and the oceans. Obviously, Newton's gravity ultimately became the bedrock of tidal math, but these historical debates show just how confusing the cosmos appeared to early scientists.
Speaking of math, let's bust a major grammar school myth right now. We've all been taught that the moon controls the tides, right? But when you actually calculate the gravitational pull using the mass of the sun and its distance to the Earth, the sun's tidal force is actually 0.45 times that of the moon. Even though the sun is millions of miles further away, its massive size means it contributes nearly half the tidal force of the moon.
Which brings us to Section 3, Spring and Neap Tides.
The absolutely crucial thing to understand here is alignment. On one hand, we have spring tides, also known as king tides. And just to be clear, this has absolutely nothing to do with the season of spring. It just means the tide is springing forth. This happens during a full or new moon when the Earth, Moon, and Sun are lined up perfectly straight, which is a phase known as syzygy. Their gravitational pulls combine like a cosmic team-up, giving us the highest high tides and the lowest low tides. On the flip side, we have neap tides, which happen during quarter moons. During these, the sun and moon are at a 90-degree right angle to each other, a position called quadrature. Basically, the sun's pull partially cancels out the moon's pull, resulting in much more moderate, weaker tides.
All right, let's get into the crazy stuff. Section 4, Earth's extreme tidal monsters.
Picture this number in your mind right now. 30 feet high. That is massive. And we aren't talking about a wave out in the deep open ocean. This is happening in a river, specifically the Qiantang River in China. When those massive spring tides we just talked about get pushed from the South China Sea into the narrowing, funnel-like shape of the river, all that water literally has nowhere to go but straight up. And it doesn't just rise slowly like water in a bathtub, it violently rushes backwards up the river at an incredible 40 kilometers per hour. This phenomenon is known as a boar tide, and the Qiantang River boar is famous worldwide, known locally as the Silver Dragon. It is literally a solid wall of water up to 30 feet high, rushing upriver, and it is strong enough to uproot trees and completely devastate anything that gets in its path.
But geography isn't the only amplifier out there. Weather plays a seriously deadly role too. Let's look at Hurricane Sandy in 2012. When a cyclone hits, the extremely low atmospheric pressure literally acts like a vacuum, allowing the ocean surface to expand upward. Now combine that low pressure with an astronomical high tide and add screaming storm winds on top. The result? A catastrophic 17-foot storm surge, literally the height of a 2-story building, crashing into the mid-Atlantic and northeastern United States. It flooded coastlines for miles inland and is a stark reminder of how deadly a high tide becomes when weather manipulates it.
We see similar localized geographical extremes in other parts of the world too. Up in Turnagain Arm, Alaska, just outside Anchorage, and famously in the Bay of Fundy, you have these shallow, funnel-shaped coastlines that trap the incoming water. This creates an awe-inspiring 10-meter, that is over 30 feet, difference between low and high tide in just a matter of hours. The water rushes in so unbelievably fast, you can physically stand there and watch the tide advancing. And finally, Section 5, Harnessing Limitless Ocean Energy. So with all that incredible power, how do we use it? Well, first, we have to look at their predictability. Coastlines experience very specific daily rhythms. You have diurnal, meaning one high and one low tide a day, semi-diurnal, with 2 equal high and low tides, or mixed, which has 2 unequal tides. The beautiful thing about these rhythms is that they are astronomically predictable months, even years in advance. Unlike wind or solar power, the tides are never going to stop, which makes them an incredibly attractive, completely inexhaustible source of renewable energy. But to capture that energy efficiently, you need the absolute right geography. Take India's Gulf of Khambat in Gujarat. Thanks to its unique funnel-shaped topography, it boasts the highest tidal range in all of India, reaching up to an 11 to 12-meter difference. If you build a tidal barrage, which is essentially a massive dam with turbines, across a narrow opening right here, the sheer rush of water flowing in and out twice a day spins those turbines and generates massive amounts of electricity. Geographically, it's pretty much a perfect setup. Now, as amazing as that sounds, it's definitely not a flawless solution just yet. The advantages are absolutely stellar. It's highly predictable, completely inexhaustible, environmentally friendly, and water's high density means it packs a massive energetic punch compared to wind. However, the disadvantages are seriously holding us back right now. The construction costs for these tidal barrages are astronomical. Plus, they are strictly limited to very specific geographic locations, like the Gulf of Khambat. And maybe most importantly, placing giant spinning turbines in narrow underwater straits can have a seriously negative impact on migrating marine life. So it's a super promising but highly challenging frontier. Which leaves us with one pretty massive final thought. Today, we've traced the tides from the gravitational pull of the moon and the sun through some wild historical vortex theories, right down to the 40-kilometer-per-hour Silver Dragon and our modern quest for clean energy. The sheer scale of this planetary waterworks is just breathtaking. The real question is, will we eventually master the cosmic pulse of the tides to power our future? Or will we forever remain at the mercy of its incredible, unyielding force? Thank you so much for joining me for this explainer. Keep wondering, keep learning, and I'll catch you next time.